Hello everyone, this is Lab 3, Finding the Mass of a Black Hole. The objective of this lab is to calculate the mass of a black hole using the information given. For Labs 1 and 2, I was given some information and by using Tracker, Python, and VIDLE, I was able to obtain the forces acting on the object and the future motion of the object. For this lab, I will reverse this process, meaning I have been given the object's motion and forces acting on it to find the mass of the black hole. The result of the mass of the black hole came to be equal to 2.3853 e to the 31st kilograms. For the third physics lab, I'm going to find the mass of the black hole using the following physics principles: Newton's second law and the momentum principle. Newton's second law being force equals mass times acceleration, and the momentum principle being momentum equal to mass times delta v for velocity. By applying Newton's second law and the momentum principle, I was able to analyze and get the mass of the black hole. In this lab, I will also use the formulas for velocity and displacement. By using these principles, I was able to get the derivative form of the momentum, which came out to be F net equals dp dt equals delta p over delta t, meaning the change in momentum, which is the effect, is equal to the net force acting on an object times the duration of the interaction, which is the cos. Also, by applying Newton's second law of universal gravitation, I used gravitation G equal to 6.67 e to the negative 11 newtons meter squared over kilogram squared. Newton's law of universal gravitation states that there is a force of attraction in all masses of the universe. In order to find the mass of the black hole, I used the following formula using G. The magnitude of F net is equal to G times the mass of the star minus the mass of the black hole over the displacement's magnitude squared. In order to put this formula into VIDLE, I used the following code. To begin this lab, I was given the motion of the object, in this case the star, in a CSV file. This file contained the x and y values for the motion around the black hole. The mass of the star equal to 1.989 e to the 27th kilograms. The position of the black hole equal to negative 2 e to the 10th, 1 e to the 10th, 0 meters. The time traveled being 1 Earth day equal to 86,400 seconds, and the initial time being 0 seconds. Applying this information to the code was relatively easy once all the information was gathered. On the code, in the visualization and graph setup, I added the black hole. In system properties and data, I changed the values to the information given. This means I placed the value for the mass of the star, the initial position of the black hole, and the delta t time traveled in seconds. Under import position data, I obtained the CSV file and added it to the code. To find the velocity in the x direction, I set delta x to be equal to x index plus 1 minus x index, and got the x velocity to be equal to delta x over delta t. To find the velocity in the y direction, I set delta y similar to what I did with delta x and x vel, but with the y values. Once I determined the x and y components of the velocity, I used them to find the initial velocity and final velocity components. By using the momentum principle and Newton's second law, I determined the initial and final momentums. After that, I calculated the star's change in velocity and change in momentum by placing v final minus v initial equal to delta v and p final minus p initial equal to delta p. Then, by using Newton's second law, I calculated that F net is equal to dp dt. Recall that earlier I mentioned how to find it. Also, by finding F net equal to dp dt and knowing that F net is the sum of all forces, then we need to find F net parallel and F net perpendicular. To find F net parallel, I found that P hat is equal to P initial divided by the magnitude of P initial. In the end, the parallel force was found to be equal to dp dt parallel equals to d magnitude of P over dt times P hat. To calculate the perpendicular force, I used dp dt perpendicular to be equal to dp dt minus dp dt parallel. I added the gravitational force to the code and the formula to find the mass of the black hole. I changed the number in the arrow scale in order to have a good view of the trajectory of the star and the forces interacting on it. And I also labeled the forces. At last, I asked the program to print the forces as well as the mass of the black hole. When we run the program, we have a good model that shows how the star orbited around the black hole. Notice that as the arrows get closer to the black hole, the magnitude changes. This is because as they are nearer to the black hole, the pull is greater than when the star is far. Now for the questions. What does it mean? This means that there are different forces acting on the object. When objects or systems are moving at an angle or incline, we have to consider the perpendicular and parallel forces interacting with the system. If the system is slowing down or speeding up, the parallel dp dt will be determined by delta p over delta t times p hat. Fnet parallel is equal to dp dt parallel, and Fnet perpendicular is equal to dp dt perpendicular, but different in the way that it's calculated and taking into consideration p hat. dp dt tells us how the star moves, not affecting the star's motion, whereas Fnet is also affecting the star's motion. What if the black hole was replaced by a different black hole? If everything remains the same except for the black hole, it means that the position remains the same and the forces are the same and dp dt will remain the same. So it is more likely that the mass of the black hole will remain the same, even though it's a different black hole from the original one. If the motion being changed means similar path but different points, then the mass of the new black hole may be calculated.